Hello everyone, we are from
International class,
and we'd like to invite you to imagine a complex transformation.
a factor that stays on the same direction even after repeated transformation.
That phenomenon is a foundation of today's topic.
Eigenvalue and eigenvector.
Let's
Begin!
Okay, so first we need to read about the introduction to eigenvalues. So, eigenvalue describe how a matrix scales a vector in a fixed direction. And here we have how to compute a lambda and non-trivial solution required. And here about the charismatic polynomial. And next we're going to the example of eigenvalue.
Okay, here I will explain the eigenvalue of 2 multiplied by 2 matrix. So here I have matrix A, B, C, D. So with this matrix, I have a characteristics polynomial. It's lambda squared minus A plus D lambda plus AD minus BC equals to 0. But we know this is a trace form matrix A, and this is a determinant for matrix A. I have a matrix A. It's 3, 2, 1, 4. And we're using the characteristics polynomial using this. We get lambda squared minus 7 lambda plus 10 equals to 0. Okay, so we got 2 lambda. So here we got it.
Next, we're going to eigenvalue of a 3 by 3 matrix. But we have to read this first.
From matrix 2 by 2, we move to matrix 3 by 3 and the determinant of 3 by 3 matrix. Determinant A minus lambda A from 3 by 3 matrix. Of course, it became a larger expression. To find an eigenvector from the eigenvalues, we need to find the determinant A minus lambda E minus lambda. This one, the A minus lambda in every diagonal, and the rest of the entries unchanged. The diagonal minus by lambda. We solve the equation A minus lambda I multiplied by V equals to 0. We have an example. So we get P lambda as this diagonal we need to. That's why in every null space, if we have a diagonal 1, 2, also 3, we can get it quickly as a 1, 2, also 3.
Next, we're going to eigenvectors. Here about the concept of eigenvector. It's like what we explained it before.
So now let's compute about the eigenvector lambda equals to 5. Okay, at the first we have a matrix A, right? So for the A minus to 5i, we got here you write the x and y, and we can choose the first row or the second row. So I will choose the first row. It's equals to 0. Y equals to x. Y equals to 2x. Y equals to 2x. Divide by 2. So we can write like this. We got the y is 1 and x is 1.
Let's move from the 2 by 2 matrix into the 3 by 3 matrix. If we have a E equals to matrix 2, 0, 0, 0, 2, 0, 0, 0, 5, which means we have this diagonal matrix. Solve the lambda 2. What is the equation? We have the lambda 2 minus the lambda is 2. And also we have the second row 2 also minus by 2. And the third row we have 5 minus 2. In here we got the 0, also this one 3. 0, we put this, and 3z. 3z, which means 0 and 0 is z. So the conversion is 2. Small.
Next, let's try about the practice problems.
We have the first question as a matrix 2 by 2. We got the determinant A minus lambda I equals to, remember, the first diagonal ratio minus by lambda. Here we got lambda square minus 7 lambda plus 12 minus 2 equals to 0. And I got this 7 lambda plus 10 equals to 0. The factorization, we got lambda, we got 2. Let's try just the first lambda. Of course, we have a minus 5I equals to, but here we can just change into the 5. 4 minus 5 from where? From this one, this 4 minus 5, and also 3 minus 5. 4 minus 5 minus 1, 2 is same. So we just change the diagonal, and the others entries have the same unchanged. It's 1, and 3 minus 5 is minus 2. We got x also y. Just take the first row. You can also take the second row. So minus x equals to minus 2y. X equals to 2y. B equals to 2 and y. From where? From 2x and first y.
Okay, so for the second problems, we have to find all the eigenvalues. We already tell you about how to find all eigenvalue at 3 by 3, right? So we can see here the diagonal is already given the value of the eigenvalues. So the value that will be 1, 3, and 1.
Okay guys, that's our presentation today about eigenvalues and eigenvector. Hope you get it and
May you understand from our explanation about eigenvalue and eigenvector. I'm Eka.
I'm Melfi. We say goodbye.